Today we'll be discussing in brief the role of anchor nodes in network evolution. So I'll be discussing what is anchor nodes and how it can be used or can be utilized to transform a regular network to some other network like small world network. I think you all already have some idea about what is a small world network. So like small world network, some other kind of networks are also there. So here I will be only focusing on how to identify anchor nodes and how anchor nodes plays a key role in the network evolution. So in today's topic, I will be discussing these 4 points in brief. So first, I will be discussing the evolution of a linear network through link addition. I think already you have some idea about network transformation through link addition in some of your prior classes, but I will try to give a brief introduction to that because it will be used as uh, the stage for understanding what is an anchor node. Then it will be followed by the analytical derivation of the anchor nodes. So we will be mostly focusing on a linear topology like a string network or line network, whatever you can say. And when we will be seeing the evolution of such network to small world network through different strategy by which we can add several links, and gradually we'll see with some like particular identification of some nodes, it will be evolved over the time when we will be implementing some deterministic link addition on a network string. So in the second part, in this analytical identification of anchor nodes, we will be discussing how we have identified this particular position that we found through like simulation that validates that will be validated through this mathematical derivation. Then if time permits, I will touch other two. That is the number 3. That is one simple example application of anchor node where we'll be discussing a very novel link addition strategy that can be very easily be implemented in a large string topology network. And at last, I will touch a few open research issues that can be handled by identifying anchor nodes as a part of solving that particular problem. So let me first start with the evolution of linear networks through link addition, where mostly I will be going through pure random link addition. I think already pure random link addition is already been covered in your class. And it will be followed by deterministic link addition, where I will be mostly discussing optimal and near optimal strategies to add links. But before starting that, as we will be using a metric called average path length to identify a pair of nodes where we can add a link. So first let me describe in detail what is average path length. So it actually estimates the shortest path between two nodes, which is average over the network. So here we have seen for a network G, the path length has been identified, and this particular equation where we have seen it is n is the n node network, and in this particular expression we have assumed this is a directional network. So if it is a non-directional network, so instead of 1 in the numerator it will be 2, so it will be n into n minus 1 by 2. So in this expression we have seen two parts. one is like summation over d of ij, another is summation over c of ij. Here c is if the network is a weighted network. Weighted network means the link has certain weights. For dij it is like an unweighted network, like it is like all are unit weight network. So let us see one simple example. So this is a 6-node network and it is a weighted network. So we have identified this network adjacency matrix with Cij, where like each entry is designating the weight of that particular link. So for example, here we have seen say V5 to V4. So here if you see the row V5 and go to column V4, it is showing 1. That means the weight of V5 and V4 is 1. So in that case, when we are calculating the total path length, so what we are doing, we are adding all the rows and then we are dividing with all possibilities like n into n minus 1. So here we can see on an average it is 1.33 hops to go from any node to any other node in this network. So as the average path length is minimum, that means the network is bit like robust in nature. So that if a network where the average path length is high, in that case what will happen, there will be a chance of like network hazard. Maybe if one of the links will be broken, as a result of that the network can be like will be broken into multiple parts. So just to avoid that, we can add a few links to make this robust. So one of the best possibility is to add a link based on pure random decision. So in this pure random decision, what we are doing, we are like randomly identifying a pair of nodes and we are adding a link between that. So here in this algorithm, we can see that in the like line 3 of this algorithm you are seeing this. So we are adding a link between u and v, node u and node v, which is randomly been taken, and obviously we are assuming that this u and v is not already been connected beforehand. So if it is already been connected, obviously this pair will not be considered because we are not considered any parallel edges while connecting a link in the network. So the time complexity to add like k number of LLs is only order of k, because we are just simply identifying two like nodes and then just adding a link. So it is very easy. So here is a simple example where we have shown in a 40-node network, we have added nearly 6 long links in a random fashion. So for each of the link addition, we have given average path length value and highest never degree. So here highest never degree means what is the maximum value of a node, which is like how many like links are connected to that node in the network. So here we have seen after even 6 link addition, the highest never degree is only 3. So mostly as like all nodes are being picked up randomly, so there is no such like identification of a like clear like a particular node or a clear region. So that's why like we are identifying two nodes and just simply adding a link if it is not already being connected. So on the other hand, if we will go for deterministic link addition, so here deterministic means in this particular case, we are trying to optimize, either maximize or minimize some of the parameters. So in our today's discussion, we are mostly like concentrated on average path length. So here we are trying to minimizing average path length. So actually we are trying to minimize, like we are trying to make the network more robust in nature, because as you have seen in this kind of like path network or like string network, like every node is only connected to the next node. So if one of the link is broken, the network will be divided into two parts. So if two links are broken, it will be divided into three parts. So it is like very like non-robust network. So if we are adding a few links, so obviously the network robustness will be increased. But in this particular case, when we have seen when we are adding in a random fashion, obviously the network average path length is getting like decreased, but not in that way. So here we are trying to like focusing on minimizing average path length with some determinism. So here we can use either optimal link addition strategy or near optimal. So first I will be discussing optimal, and then I will be discussing why near optimal link addition is necessary to like realize this particular link addition strategy. So first, let me discuss this optimal link addition. Here we are, what we are doing. So for example, if we have to add, say for example, two links in a network, then what we are doing, we need to add both the links together so that overall average path length of the network can be minimized. So means if you have 10 links to be added, so 10 link you need to add at a stretch, not one by one, not sequentially. It is optimal. So you need to add everything together so as to get the minimum value of APL. So as a result of that, if you see the time complexity is too high, it is like n to the power 2k plus 2 log n. So if even if the k value is the simple 5, maybe like that means you are adding only 5 links, then it is becoming n to the power like 12 log n. So if n is like 100 node network, then you can understand it is 100 to the power 12 log n. This is the time complexity to just add 5 links in a network. So it is very difficult to realize in real world. So that's why we shifted to near optimal, where instead of adding all those links deterministically together, we are adding sequentially. That means if I have to add 5 links, I will be adding the first one. That will give me the lowest possible APL. Then I will be going for the second one, and sequentially third one, fourth one, and fifth one. As a result of that, it cannot, like it may not be as optimal as this particular algorithm may give, but that will be much faster. So here only difference is, instead of adding all the links together, we are adding one by one in a sequence. So as a result of that, you can see the time complexity has reduced to only k into n to the power 4 log n. So even if it is very large, if like n size is very large, for example, it is like 1000 node network, it is like 1000 to the power 4 log n. But still it is much lower than the optimal case, because in optimal case, if it is 1000 node network and we are adding, say for example 5, it is like 1000 to the power 12 then log n. It is very difficult. So let us see if we are using this near, that is like sequentially we are adding one by one link in a network, in a string topology network, to make this network more robust and try to optimize the average path length value. So here we can see gradually the average path length is reducing very drastically with respect to the random link addition. But on top of that, here you can see the next value, that is called HND. So here you can see in A, B, and C that HND value for each link addition, it is continuously increasing. So 3, then after, like if you see B, when it is like 2 link, it is getting 4. When it is 6 link, one of the nodes are getting like highest neighbor degree is becoming 8. So one of the nodes in that particular link addition is attracting more number of links in a network. And the main thing we have seen while experimenting with this near optimal link addition algorithm, that the first link, that is the LL1, that you can see the top figure, the LL1, that is long link 1, is connected in between node number 8 and node number 32 in this 40 node network. So if you will see, if 40 is n value, so 8 is nothing but 0.2 n. So if n is 40, so 0.2 of 40 is 8, and 0.8 of 40 is 32. So we have seen in an end node network, if we are adding a link based on minimizing the average path length, that will minimize the average path length, we'll always see that the first link will always be added between 0.2n and 0.8n of an n node network. Obviously, the size of the network should be at least 10 or above. So less than 10, you may not have that deviation, but once it is like minimum size of the network is minimum 10 or above, or in any time when you are adding a deterministic link to reduce the average path length, always you will find the first link is always connected between 0.2n and 0.8n of an n node network, and over the time one of these two nodes, either node 8 or node 32 in this 40 node network, will attract other links over the time. So here we have shown with 32 node. So it may also happen that once the second, if the second link will connect between like node 8 and some other node, then obviously the next link also will be attracted by node 8, not by node 32. And over the time, if there is no such uh, like uh, bar on the length of a link, so length of a link can be anything. In that case, until and unless one of those two nodes which is started attracting many links, when it will be fully connected to all other nodes, then the other node will be picked up. Until now, anyone has any question? Hello?
No, sir.
Okay.
No, sir.
So here we can see until this slide that when we are adding a link, deterministic link based on some particular parameter. So here we are like minimizing average path length. Obviously, over the time, one of the links which is being connected by long link 1 will attract other nodes. So here we are calling this node anchor node because it is actually anchoring other links in that network when we are adding the link in a deterministic way. So we named this particular node pair as the anchor nodes. So that doesn't mean that these two nodes are only the anchor nodes. So for example, if there is no such like upper bar on the length of a long link, so when say for example this node 32 will be connected to all other links, maybe the next node, maybe node 8 will be picked up the next set of links, and when node 8 will be fully connected to all other links in the network, then some other link will becoming an anchor node. So here we are trying to see why always the first long link is connected between 0.2 and 0.8 n. So that first link is always very like we have seen very clear identification of the nodes in any large network. So from here we are shifting to this analytical derivation of that anchor node. So whatever we have seen through simulation study, we tried to identify whether if we will implement this entire philosophy into a mathematical setting, whether still we are getting such kind of observation. So just to see that, we went for this analytical identification of anchor nodes. So to do that, what we have done, we have taken a unit length string. So here the unit length string is nothing but a network where we are assuming that the number of nodes, that is n, is almost tends to infinity. So it will become a limit of sequence of multiple nodes where maybe between two nodes the distance is always 1 by n. If it is n, like n is like total number of nodes. So as n tends to infinity, it is almost, we can assume that it is a linear string and it is a continuous one. So our like rest of the derivations will be based on these assumptions. This network is a unit string and there are n number of nodes where n tends to infinity, and as a result of that the distance between two nodes are always 1 by n. And if you are adding a long range link, it is also almost like 1 by n, and that doesn't matter. When it is like scaling, it will give you the same result. So in this particular case, what we did, we tried to optimize the average path length, and in this particular setting, we are trying to add a long link between, say for example, point P1 and P2. So we are trying to identify what should be the optimal value of P1 and optimal value of P2 in this unit string network, where here S is the source node and D is the destination node, and the distance between source node and destination node Bx. So that is the experimental setting. So until now it is clear. Hello.
So analytically, we are talking like connecting two nodes. Like, how can we realize this physically?
Could you please repeat your question?
So analytically, we are talking like connecting two nodes and using a long link. Like, how can we realize this physically?
Physically means in a mathematical setting.
No, sir, like in a real world situation.
So two nodes can be anything. Say for example, there is a highway, right? So in a highway, if you are say deploying a few like high range Wi-Fi devices, highways are mostly like you can mimic a highway like a string topology.
You are talking about wireless network. This is a wireless network, Venkat. So you have a long string-like wireless network where you can have long-range radios to have long links.
Oh, okay, sir. So how can we realize this in a social network?
Social network will have a different identification. I will come to that. I will come to that. So please like keep your question with you, because let me first finish this derivation. Discussing
Okay.
this derivation, I will come back to you in that social network aspect, that how we
Okay.
can realize this long range link. Okay.
Yes,
Please remind. Please remind me if I will forget. So in this particular setting, until now it is clear, right? How we have set this particular mathematical environment. Because if it is not clear, then the rest of the part will be difficult to understand. Or any one of you have any doubt in this mathematical setting that we have used this unit string network, where we are trying to add a link between P1 and P2, and our objective is to optimize the value of P1 and P2 so that we can get the actual location of P1 and P2 after adding a link, where S is the source, all possible sources, and D is all possible destinations. And this distance between source and destination is X. Is it clear?
Yes, sir.
Okay. So here to minimize the average path length, if you see the path length, average path length expression, there was a term like where we have divided all possible like source destination distance divided by n into n minus 1, and if it is like undirected, it is n into n minus 1 by 2. But this n into n minus 1 or n into n minus 1 by 2, these are all are like fixed term, like constant term. So if we can minimize the end-to-end path distance, so the average path length also will be minimized, because at the end, after adding all such possibilities, we are simply dividing by a constant to get APL. So in this particular derivation, we are trying to minimize the path length, total path length for all possible source and destination pair. And when we are adding a link between point P1 and point P2. So for this particular thing, we can see this equation 1, where there is double integral is there. Double integral only because of the location. The first integral talks about the source. So source node can be in between 0 to 1. So any point it can be there. So any point can be a source node, and for each source, all others will be destination node. And here we have assumed that all destination nodes are at the right side of the source node. So for this particular figure, if you'll see, when we are seeing the destination node, we are not seeing the left side of S. Like in between 0 and S, we are not looking for any destination. So here we have assumed that all destinations are at the right side. So it is just to simplify the mathematical notations. Otherwise, it will become more complicated, but at the end, we'll get the same result. So if you'll see, there is a long link connectivity between node P1 and node P2. So actually, this particular unit string is subdivided into 3 parts. One is from 0 to P1, another is P1 to P2, another is P2 to P1. So actually the shortest path between all such source and destination possibilities is nothing but the all sum from all these 3 subdivisions. So 0 to P1, P1 to P2 and P2 to 1. So if we can identify the total length, path length contribution from these 3 segments and we'll add, then we'll get the total path length contribution from the entire string of unity. And if we can minimize that particular expression, obviously we'll get the minimum value of P1 and P2, as the entire function is a function of P and X, where X is nothing but D minus S. So here just we did that change of variable, otherwise it will be like 3 variables, P, S, then D, then something else. So just we did change of variable, because if it is a function of S and X, obviously X is nothing but D minus S. So here we are trying to optimize this total path length contribution. So let us see the first case. In case 1, here we are assuming the source node is in between 0 and P1. So don't see this expression, try to understand from this figure. So here source is between 0 to P1, and destination for this particular source node, destination will have 3 possibilities, right? Either this destination D can be between 0 and P1, or it can be between P1 and P2, or it can be between P2 and 1, right? So for this particular segment, that's why we have 3 different cases. So either D is between 0 and P1, so the first case. The second case is between P1 and P2, the second case, and the third case between P2 and P1, that is the third case. So here how we are getting this minimum, it is a bit tricky, but I just want to give a simple explanation of the first minimum that we that we mentioned here. So here we are showing that when S plus X, that means D is between P1 and P2, then how I can reach from source to D when this link is already connected? So there are 2 possibilities. Either the distance between source and destination in a linear string itself is the shortest, so we will go with X. Otherwise, it may go like that. It will go from S to P1, then take this particular like long range link, it will reach P2, then it will come back to D. So the second part is showing that it is going to P1 minus S. So P1 minus S, it is traversing this one. Then the next one is P2. So it is going from P1 to P2. Then it is coming back to S plus X until D. Do you have any like doubt in that? Hello?
Sir, can you repeat it, sir?
So actually the case one, so if you'll see the previous one, as I told, we have to minimize this particular equation 1. So to do that, we have a source and a destination. We just make some change of variable by introducing x, where x is nothing but d minus s. So here you can understand this particular expression, but the first integral is for the source and the second integral is for the destination location. And as we have added this particular link between P1 and P2, actually we are dividing into 3 segments. Until this, it is clear, right?
Yes, sir.
So next, when we are coming for case 1, so here we are assuming that the source is in between 0 and P1. Now, when source is in between 0 and P1, destination can be in any of this particular segment, right? We have no control over the destination, because we are computing all pair shortest path, right? Is it clear?
Yes, sir.
So when, say for example, when the first part, when destination is between the first pair, so between 0 and P1, so obviously it will not use this long link, right? It will directly go to the destination. That's why when this S plus X less than equal to P1, S plus X is nothing but D. When D is in between 0 and P1, obviously the shortest path is only X. So only you have to traverse X to reach D, right?
Yes.
The next part, when D is in between P1 and P2, so you have 2 possibilities. Either your direct distance is minimum, so you can directly go through this traditional link from S to D without using this long link. Or maybe D is somewhere where if you will use this long link, you will reach faster. So that's why when D is in between P1 and P2, you have 2 possible options to reach D in this particular figure. So that's why we need to take this minimum of this. So whichever will be minimum, I will use that because it is like shortest path. So either it will be X or it will be this expression. So how this expression came? So just check this expression, P1 minus S. So P1 minus S is the distance to reach P1 from node S. Understood?
Yes, sir.
Then you are going to P2 and then coming back to particular this distance, S plus X. Is it clear?
Yes, sir.
So you need to take minimum of these 2 when D is in between this P1 and P2. Now the third possibility, when D is between P2 and P1. In that case, obviously you will use this long link because it is obviously will give you H. So it is directly you are going to P1 minus S, going to P2 and then directly go to D. This is the last part. So here the trick is why this S plus X minus P2, or here the trick is P2 minus S plus X, because the second case you are reaching P2, then you are coming back. That's why it is minus. In this particular case, D is like location of D is higher than P2. That's why it is like S plus X minus P2, the distance covered. Is it clear?
Yes, sir.
So in this particular case, when S is between 0 and P1, D will have these three options, and for each option we have identified these three. So what will happen once we have identified, then we need to just go for 0 to P1 because S is within 0 to P1 as we have seen earlier. And the second one, D can be between 0 to 1 minus S anywhere, because as we have identified, destination is always at the right side of S. That's why we have taken 1 minus S in the second integral. Is it clear? Equation 2 is clear. Any doubt?
It's clear, sir. You can proceed.
Any doubt is there for equation 2?
Clear, sir.
Okay, so we have just calculated all such possibilities. When we are calculating the second integral, there can be like when it is nearby P1. So you can see when D will be nearer to P1, obviously it will use this direct way. When it is nearer to P2, it will use this way. The same thing here we have just calculated. When it is direct, it is X. When it is like less than half, it is still X. Then it is going to the next version. And when D value is some other part, obviously it will use the long link. So this is for the first case. Second case, similarly we are doing that. So here S is between P2, P1 and P2. So obviously we are only calculating all possible locations of D at the right side of S. And based on that, that's why we have only two cases. Either it is between P1 and P2 or it is P2 and 1. So here, similarly, we have calculated. So if you have any doubt, you can ask me later. So I will share this PDF with all of you. So the same thing we have done. So now S is from P1 to P2 as per equation 3. And for all 0 to 1 minus S, we are calculating all D's. Then based on those locations, we are just simply identifying what to be put as the argument. The same is 3. When S is at in between P2 and 1, obviously there is no other option than to just use the X, because as D will be always at the right side of the S, so never it will use the long link. So in any case, it will be only X, dx, ds. So when we have got these three cases, we have added these three cases to get the optimization function. So our actual problem was to minimize the average path length, and as average path length is nothing but the total path length divided by all possibilities like n into n minus 1 by 2 or n into n minus 1 for directed network. So as that part is constant, we are not again here, we are not considering that. So we are trying to do like minimizing this P1 and P2, where P1 is less than P2. And we solved this, and we also got that the P1 optimal value of P1 and P2 are 0.2071 and 0.7929, whatever we have seen in our like simulation setting. Like always, the first link is connected between 0.2n and 0.8n. So here we have analytically solved that particular location, and we have seen, okay, for analytical derivation also it is coming similar. So actually whatever we have observed through simulation, that was correct. But what is the reason that suddenly this 0.2n and 0.8n was picked up? So for that we tried to see if we have a like a ring network and we want to run the same thing to just to minimize average path length. So where to connect? We have seen it is connected between 0.25 and 0.75 in an n node network. But whenever say one of the links, say here we have removed one link between 1 and n, so obviously it is becoming a string. Then we have seen this point from 0.75 to 0.25, it has shifted to 0.8 and 0.2. So what is the actual reason that when a ring is becoming string topology but removing one link, why this long range location is shifting. So to understand that, we have seen this path length contribution. So whatever until now we have seen in unit string, if in actual value we are calculating that all possible path length in actual network, we can see this path length contribution from 1 to 0.2n, then 0.2n to 0.8n, and 0.8n to n. That is like 3 segment when we are connecting a link. So if we have seen for different set of networks, we have seen, if you see this path length contribution 0.2 to 0.8n, that is the in between this long range link, you can see it is almost like 54% almost of total path length contribution. And as the terminal nodes, so as in it, so for example, here if it is a 20 node network, terminal node is which is nearer to like 20, they are like contributing more path length than the mid node in a network, because from mid node you can reach other node very easily, but if it is some terminal node, you need to go all the hops to reach that node. So here when we have seen the actual path length contribution, it was clear that why this suddenly the first link is always trying to find out some like nearer to terminal node. That's why it is 0.2 and 0.8. It is almost nearer to the extreme nodes in a string topology, where like there are no other paths existing. It is the like one of the simplest topology you can assume. So by seeing that, we can see a very simple example. If by seeing this observation, that if we can, as we have seen through simulation, okay, these anchor nodes can be formed in a string topology, and also we have seen through like analytical derivation, like yes, it is existing. So if we can apply directly to transform a network to a small world network, what we can do, we can simply use this particular observation to get a very faster like network deployment. As we have seen in like near optimal case, for an n node network, it is like n to the power 4 log n time complex to add a single link. So even if like n value is, for example, like 10,000, it is like 10,000 to the power 4 log n. That much time on an average it will take to like run the entire code to give you a particular set of value where to add a link. So when we need to do something like in a like a disaster response scenario or something tactical network deployment in such like string topology, so we don't have that much time to identify where to add, say if you had to add like 10 links to make it like faster, faster ad hoc network. So where you will add? So to deterministically add, you need to go for like this n to the power 4 log n to add each of the links. So if k links are there, it is like k into n to the power 4 log n. So here comes the heuristic, where we can use this observation from this optimal link addition, near optimal link addition, by plugging into this particular anchor node concept to get a very like efficient heuristic design. So here we are talking about one heuristic. Such heuristics called sequential deterministic LL addition, or SDLA. Why sequential? Obviously, we are seeing the observations from near optimal, which is actually sequential link addition. And what we have done, we are adding the first link between 0.2 and 0.8n, and we make this 0.8n as the anchor node. And the rest of the links are based on span distance. So let us see what we talked about until now. So for example, this is a 30 node network. So when it is 30 node network, 0.2n and 0.8n are nothing but node 6 and node 24. So first link is now added. There is nothing because we know it is anchor node and it is always fixed. So we have added first link. Now maybe you have to add more links in a network to make it like more robust and more like less APL for such kind of applications like disaster response scenario or tactical network deployment or something like that. So now we have again three part. So we call it span distance. Span distance is nothing but the distance between this particular first slot, the second slot, and the third slot. Here that is dist 1 and 5, as we have taken all unit length network. So here like all link weight is only unity. So the first weight is so from here we are starting with span distance calculation. So we are going from here to the first slot, it is only 5. Then in between it is how much? 18. And the third one is how much? 6. So here we have seen after addition of the first link, long link between the anchor nodes, there are 3 segments with different span distance. So in our algorithm, what will happen? We'll take the high span distance into account and we'll take node 0.8n as we mentioned previously as the anchor node, which will anchor other links in the network. And what will happen? We'll again divide the highest span distance by 2. So here it is 15. So if you'll see now like 18 is divided into 9 and 9. And then we'll add the second link. Now what will happen in the next run? Now it has 4 segment, 1 to 6, 6 to 15, 15 to 24, 24 to 30. So what will happen? Again it will check all. So now you have like in between 2 segments with 9 span distance. So then what will happen? We'll take the first occurrence of the high span distance. So maybe we'll take 6 and 15 into account and then we'll divide 6 and 15 into half. As it is 9, we will take the like ceiling value, it will be like 5. So 6 and 5, it will be like almost 11. So next link will be added between 24 and 11. Now it will be again span distance will be calculating like 1 to 6, then 6 to 11, 11 to 15, 15 to 24. So next it will be between like 15 and 20. So next will be we'll see the next highest span distance will be between 15 and 24. That is again 9. We'll make it half. It will be node 20. The fourth link will be added between 24 and 20. Now again it will start calculating from first. So for each iteration it will identify the span distance and with the high span distance it will divide it into half and add that half node which is identified as the half of that particular span distance. It will be connected to the particular that 0.8n node. So it is very like efficient. For k number of link addition, it is like only k into n order of complexity. And here we are showing that the first one is based on your near optimal link addition that we have shown previously, that how we are using that algorithm sequentially we are adding. The second one is based on this SDLA. So almost you can see almost similar way it has been connected. And when we have seen some results, we can see the maximum deviation is only 6.33%. So that is very nice actually for a very large network. And the deviation is also very less, minimum deviation with respect to SDLA with near optimal. So actually SDLA performs very good and with only like order of n time complexity to add only one link, whereas near optimal is almost like n to the power 4 log n to add one link. So for like a large network, SDLA performs very high. So at last, I want to just give some idea of some of the open research issues that if you want, you can work on or do something related to this. If you want to use this anchor node concept into account. So another big thing is to identify in a 2D network or maybe 3D network, because still in 2D network, we did not find such kind of like particular node. Like here in a string topology, we have found like 0.2n and 0.8n, but for 2D network, it is difficult to identify like where that particular anchor will come. Because if we can identify some anchor node into account, we can go for like very novel heuristic design based on that anchor node. Also, like here we have only talked about average path length, but if you will apply some other metric, some like some centrality metric or some maybe clustering coefficient or some any other metric, so based on that maybe the anchor node will be started shifting. So how it will work, that is also can be like studied. Also, we can use this concept of anchor node to design efficient and easy to deploy ad hoc and tactical network. So one of the example already we have seen in terms of designing this SDLA heuristic. Another can be like designing robust and ubiquitous like community broadband network. Community broadband network, maybe it can be like highway, it can be a small rural setting where like we can like create such kind of like either string or some 2D topology, and we can identify some anchor points which can be used as a gateway node that should talk to the internet cloud, and like that identification of anchor node can be very efficient in such setting. Then also designing fault tolerant next generation networks, like if you are talking about say 5G networks and others. So in those cases, like as you know, 5G will mostly implement all the functionalities as a like virtual network. So it will be like mostly installed in clouds, and those or any like containers or maybe some substrate network. And the main problem will be to add like multiple such virtual functions in a chain to create a particular end-to-end service. So if we can know some particular anchor nodes or like some critical point in a network, we can manage the way those particular functions can be deployed. Also, in general, you can like design like some architecture for like better quality of service or quality of experience, like IoT, fog computing, or some SDN architecture. For each of the thing, you will see that there will be. So, for example, in SDN architecture, there will be a central controller. Now, if the architecture is distributed, now the question is, in a distributed architecture, where the central controller should sit. So to identify that point, so identifying anchor node in such setting will be very interesting. So in many of these discussions you can find in chapter 4 of this book. To be precise, it will be nearer to 4.8, section 4.8 of this book. And if you have any doubt, you can ask me.
Any questions from anybody?
So some of you asked me about social network and link addition, something related to that.
Yes, sir. Long link addition, and like how does it affect the social network?
So here long link addition, you can think of like say you know me, but you don't know my friend. But when you are connecting through me, so like in LinkedIn you are seeing, right, that first contact, second it is written. You have seen that?
Yes, sir.
So
Yes, sir.
you can think of like second or third as the long link. So in a 3 or second hop, you are connecting, you are sending friend request and that person is accepting that request. So you are creating a link out of that. So when you are creating a link out of that, maybe in your profile, it is showing someone's profile as like third hop. Now you are my friend. Now I can also see that person as second hop now. So it has reduced. So actually you have created a link and because of that, my distance from that particular person has reduced. The same thing is happening in this particular examples that I was discussing. So when we are adding a link, using that link, we are reaching faster to some distant node.